Hello and welcome to my first video on this channel. It's going to be the first video on the series of the n particle system. So we're just going to delve really deep into it, develop all the formulations for it, all the theories and whatnot. So the series isn't really going to be about specific examples, or so to speak. Or we're just going to be developing the formulations. Like we're going to develop Newton's formulation, the energy formulation, and all that stuff, and then eventually the Lagrangian formulation, which I hope to do on this series as well. But we're not really going to be going over specific examples, whatnot. Maybe I will if they reveal like a lot about the subject, but for now, let's just delve right into it. So the n-particle system is probably one of the most general systems you can discuss, at least in the beginning stages of classical mechanics. They can apply to virtually anything as long as you can neglect the rotation of these objects, so they don't really affect the motion, at least, or there is no rotation in the objects or something like that. Then you can treat it as a particle system. So yeah, so let us resolve these forces, find a way to quantify them in some way. So let's start off with particle 1 here. And hopefully the way I've drawn the arrows implies that these are actually the forces of the objects. So as you can see, these objects are interacting with forces. There's 6 arrows. They come in pairs. All those facts are going to be very useful for proving conservation of momentum, which is what I'm going to do in the next video. This is pretty much just the setup for the next video. We'll see how the way I'm going to write everything. I know it's going to be extremely complicated, kind of complicated looking, but the notation is going to reveal a lot about what is going on in a particle system, and it's pretty much going to make the derivation for the conservation of momentum a no-brainer. That's what I hope, at least. So this would be the force on 1, that's how we're going to write it, by 2. And then we are going to quantify this arrow right here as the force on 1, once again, by 3. So as you can see, we're going to write everything in this like little superscript, the interaction forces, at least in this little superscript notation, or sorry, subscript notation. We're going to have the first index, or the first indice, be the actual particle that we're interested in, and then the second one is going to be what the forces do by, or like which particle is causing that force, and that's going to be 2 in this case, in this direction, and 3 in this direction. And then although I didn't draw it, each of these particles can also have an external force, which we'll write like this. So just the external force on 1, and we'll write ext in the superscript, because there's really no other place to put it. You're never really going to be taking powers of the forces. You're just going to treat them as vectors, always. All right, sweet. So now let us quantify, or like resolve, Newton's second law with this notation. So we're going to write the net force. We're going to split the net force into 2 parts: the external force and the interaction forces. As you can see, this is Newton's second law. However, the way it's written doesn't really reveal too much detail. So let's generalize this, right? So we are going to assume we're working on particle alpha, right? So if we were working with an n-particle system, we should have n Newton's second law equations. So we can have, for example, each of these. This is going to be the net force on 1, mass 1, the acceleration of 1, and then we'll also have one for 2, and a 3, and 4. So we'll have a Newton's second law for each of the particles. We'll have n equations. This first term is just going to be the net external force on alpha. Perfect. Then the next component is going to be all the interaction terms, or all the interaction forces. Write that with the sigma notation. And we're going to use the index beta. We're going to make a condition that beta cannot equal alpha. See here. So this is all going to be the forces on alpha, because remember, this is the equation for alpha. We are interested in the particle alpha. This is going to be the force on alpha by beta. And what we're going to do is just sum all the interaction forces. And we made the condition that beta cannot equal alpha because we can't have a force act on itself, right? We can't have a force on one by one. That's just not a thing. We're going to get rid of that. And of course, that's going to be the left side. That's going to be the net force on particle alpha. So the right side is going to just be the MA. However, I'm going to write it as the derivative of the momentum. And you'll see why as well. I'm going to say this is the derivative of mass alpha times the derivative of the position with respect to time. And this R right here is just going to be the position. So let's say this is the origin here. And this is particle 1. Well, then this vector here is going to just be the position of 1. Then we'll have position of 2 up here, and the position of 3, and so on. That's just what that is. And how the position is changing with respect to time is, of course, the velocity. Mass times velocity is the momentum, and then we take the derivative momentum, which is just equal to the force. So Newton's second law could also be written as the derivative, or the time derivative of momentum. So you may ask, why am I writing it like this and not just bringing that derivative in to make it a second derivative? Well, this is just because we're going to make another generalization, or this is going to allow us to make a further generalization, and that's the fact that how the mass changes in our system does not matter. So this particle 1 could have a decreasing mass, something like this. So the derivative of mass alpha is less than 0, or it could be increasing. It could just be constant, which usually we do consider the mass to just be constant. In that case, the derivative of the mass is just 0. Then regardless of how the mass is changing in the system, the mass doesn't even have to be conserved. Like just one particle can be decreasing the mass and whatnot. You'll see that by writing it like this, we can also generalize the fact that the mass can be changing and momentum will be conserved. So yeah, so that's going to be Newton's second law. And now the only thing we're missing is Newton's third law here. And that's pretty easy to write with our notation. That's the advantage of it. It's incredibly beautiful. I guess that's a good enough arrow. So if we have the force on alpha by beta, and let's say we flip these indices, what that's going to cause is just a little negative sign up front. If we flip the indices, so the force on beta by alpha. And that should make sense. This is Newton's third law, right? So we have alpha. This is the force on alpha by beta. And this is beta. You can see it's going to be equal and opposite. That's how it is in the real world. I did not pretend to derive these equations. These are just observations made by Newton himself. And these are going to be the fundamental axioms that are going to propel us to literally the rest of quantum mechanics and pretty much the rest of physics in general. I mean, he was the man that started it all. So in the next video, we are going to derive the conservation of momentum using this, and you'll see the advantage of writing everything like this. It's going to make it clear as day. Alrighty, well, thanks for watching.